Hello, you're welcome to this class. Our topic today is congruences and related topics. Let's begin by definition. Let n be a natural number. We say that two integers a and b are congruent modulo n if n divides a minus b. We write this as a is congruent to b modulo n. By way of notation, we write a sub n to mean the congruence class modulo n that is containing a, and by Zn, we also mean the set of congruent classes modulo n. Now, this symbol for congruence is actually an equivalent relations because 1. Congruence is reflexive, is symmetric, and transitive. That makes it an equivalence relation. The set Z modulo n is a ring. In fact, a commutative ring with identity. This means that congruent classes can be added or multiplied. For example, Z4, under addition and multiplication, you have this table here. You will observe that elements of Z4 are 0, 1, 2, and 3. And all the elements that are under the table for addition and subtraction are all members of Z4. So for that reason, Z4 is closed. It's commutative as well, and it has identity. So for that reason, you said that integer modulo 4 is a commutative ring with identity. Proposition. If P is prime, then ZP is a field. That is, all non-zero elements have multiplicative inverses. So if integer modulo P, where P is a prime, is actually a field. Let's take an example to see the application of this concept. What is the inverse of 225 modulo 157? Solution. By applying the Euclidean algorithm in concert with the division algorithm, starting with A to be 225 and B to be 157, we have trying to find the GCD. We follow these steps line by line, and we observe that the GCD is 1 of 225 and 157 is 1. So what it simply means is that the pair 225 and 157 is coprime. So for that reason, we progress. It will definitely have an inverse. Because it's coprime, the inverse, it will have an inverse. But if it is not, the GCD is not coprime, then there's no need progressing further because the inverse may not exist. And even if it exists, it may not be unique. So going forward, we are going to have that the inverse of 225 modulo 157 will give us minus 30 modulo 157. And normally, we don't leave our results in negative. So converting it to positive, you have 127 modulo 157. So that is the inverse of 225 modulo 157. Linear congruence. An expression of the form ax plus b is congruent to 0 mod m, or ax is congruent to b mod m, is called a linear congruence with one unknown. Example, solve the congruence 3x congruent 4 modulo 7. Now, you will agree with me that 5 is an inverse of 3 in modulo 7, since 5 times 3 will give us 15, and 15 will be congruent to, will give us 1 modulo 7. Using this information, we can now solve this problem and break it down, and we now have x is congruent to 6 modulo 7 as the answer. Now, substituting back into the original linear congruence to check whether 6 is actually a solution, you discover that 3 times 6 will give us 18, and under modulo 7 will be congruent to 4 modulo 7. The famous little theorem. The theorem states that if P is a prime and A is a coprime to P, the GCD of AP will be coprime. Then P will divide A raised to power P minus A. This is the same as A raised to power P minus 1 being congruent to 1 modulo P. Let's see an example of how to apply that theorem. Find the remainder from the division 23 raised to power 1443 by 13. So you are going to evaluate 23 raised to power 1443 divided by 13. What are you going to get as the remainder? That's what the question is all about. Now, solution. We have that 223 raised to power 1443 will be congruent to x modulo 13. And when you move forward to find the GCD of 3 and 13, you're going to have 1, meaning the pair is a coprime. Okay, and you continue applying the Fermat's-Little theorem. We can now write that minus 3 raised to power 12 is congruent to 1 modulo 13. Further, raising the congruence to power 120 to power 1/20th, we get the following. And when you simplify further, you're going to get that the remainder will be 12 from our evaluation. Now, primitive roots. Let's begin by definition. If alpha is an element of integer star modulo n, the order of alpha is the smallest exponent k, such that alpha raised to power k will be equal to 1. That is the definition of order. Okay, now let's look at an example. We should determine the order of alpha in integer star n when n is 17 and when a is 3. Congruent class modulo 3. Now, the solution is simple. We have alpha n to be 16. Note that d is equal to 1, 2, 4, 8, 16. Is the complete list of positive divisors of phi n. The smallest element d satisfying 3 raised to power d equal to 1 is the order. Therefore, we have these evaluations here. Thus, we see that the order of alpha is 16, which is the largest possible order that the element of z integer modulo 17 star can attain. Now, let's continue. An element alpha in integer star modulo n is called primitive if the order of alpha is equal to phi n. Now, compute integer star modulo 10. It suffices to find all integers m lying between 0 and 10 that are coprime to 10. Thus, the elements will now be 1, 3, 7, and 9. To convince ourselves that Z10 is closed under the operation of multiplication, let us construct the multiplication table you're seeing here. Now, you discover that all the elements in the table are all members, all belongs to Z integer modulo 10 star, which is 1, 3, 7, 9. For that reason, it is closed. Okay, and it is also commutative. We can see that all the elements in the multiplication table are indeed in Z star modulo 10. Thank you for listening.